All right, let's talk about Newton's Law of Universal Gravitation. This was the recording that I told y'all I wanted y'all to listen to. It's in your notes. It was the part where we skipped over, and it'll help you with homework problems 8, 9, and 10. All right, any two objects in the universe exert an attractive force on each other. That force is called a gravitational force. That strength that gravitational force strength is proportional to the product of the masses. Okay, so that means if the masses go up, then the strength also goes up, and that is a multiplication issue. It is inversely proportional to the square of the distances between the two. So if we let G be the universal gravitational constant, which I would like for you to have your formula chart, your notes, and a calculator out, you'll notice that G is on the front underneath constants and conversions on your formula chart. It's a universal gravitational constant that's given to you. Also, then, if you flip over to the back side of where your equations are, underneath the mechanics section, on the second column, right underneath all of the variables identified, what the different letters mean, then you see formulas 1, 2, 3, 4, the fifth one down, and you see this formula where it says F equals Gm1m2 over r squared. So again, the product of these, if this goes up, then that makes the force go up. And then if you have this value, if this value goes up, then this value actually goes down by its squared. So you have to make sure that you don't forget that squared. Now the force is going to be in newtons because it's always in newtons. And forces are always in newtons. And then your masses will be in kilograms and your R value will be in meters. Okay? This actually came about. Henry Cavendish determined the first reasonably accurate numerical value for G more than 100 years after Newton's laws were published. It took them a while because to understand the math that had to be done to actually come up with the numbers. He did this really with these lead spheres and how they had some angular deflection because of those, that showed that there was gravitational force between those objects individually as well. And that value that he came up with is the same as the value that we can find on our formula chart. Okay, so I have the units a little bit differently here, but they all mean the same thing. It is 6.67 times 10 to the negative 11th. That's the number that you would use. And it can either be Newton meters squared over kilograms squared. Let me move this out of the way just a minute. Over kilograms squared, or it can be meters cubed over kilograms seconds squared. Either one, they're both the same thing. That's not exactly how it appears on your formula chart, but they both do mean the same thing. All right, now let's do the example that's in your note packet. What is the force of gravity acting on a 2,000 kilogram spacecraft when it orbits at 1.276 times 10 to the 7th meters from the Earth's center, which, by the way, that's about 2 times as much as the Earth itself. So what we're going to need to know is we know one of the masses. We also need to know the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. And then we need to use this radius value. And it's not the radius of the Earth, it's just how far it is from the Earth. So I don't really like that variable being listed like that. It's just the R value away from the Earth's center that the spacecraft is. So we'll use our F equals Gm1 m2 over R squared. And then we will plug in numbers. When we plug in these numbers, hopefully you have a calculator out as well, and you'll notice that I didn't use the units per se for the universal gravitational constant. Lots of times when I'm given a constant value, I won't do that, so you just need to be aware of that. Then we would have 2,000 kilograms multiplied by 5.98 times 10 to the 24th kilograms, and then we would divide that by the 1.276 times 10 to the 7th meters squared. Don't forget the squared value. That's really, really important as we move along. So you should come up with 4.899 newtons when you come up with the force of gravity acting between these two objects. Now, the important thing to understand is the equation for universal gravitation is an inverse square law. So really, the gravitational force is equivalent to 1 over the d squared. So what you need to understand is if I have a regular force of attraction that's 320 newtons, how would it be affected if my distance quadrupled? Well, that means that it's going to go up by 4. So it's going to be 4 times as much. So I would take my 320 newtons and I would say that that's going to be affected by 1 over my d squared. So I'm going to say that's going to be divided by 16 because 4 squared is going to be 16. So that gives me a value of 20 newtons. Then what happens if the distance is halved? Well, that means it's going to go down by a half, which will mean that the force is going to go up by a fourth. Okay, so if I take my 320 newtons and divide it by my 1 over d squared, well, 1 over d squared would be 1 over a fourth, not 1 over 14, excuse me. So I'd have 1 over a fourth, and when you do that math, you actually take that fourth that's on the bottom and flip it, take the reciprocal, and multiply by 4, so you'd end up with 1,280 newtons. So if we get it closer, it should go up, and so that should make sense. So again, inverse square law, really, really, really important. You'll need to know this for some multiple choice on your test. All right. So I want to derive an expression for G from the law of universal gravitation. So the law of universal gravitation formula on my formula chart is F equals Gm1 m2 divided by r squared. Well, I also know that F equals ma. I know that, and I know that that is a gravitational force using gravity as my A right there. So if I set these two forces equally each other, then I would say that G m1 m2 divided by r squared equals mass times gravity. If I want to solve for mass, then solve for gravity, then I'm going to divide by mass. And if I do that on one side, I have to do it on the other. Well, this mass is actually one of these masses, so I'm just going to cancel this mass out right there. So then I end up with an equation of Gm over r squared equals gravity. So if you look on your formula chart, you look right at the formula of universal gravitation, which is our F equals Gm1 m2 over r squared, you'll notice right below it that it says G equals F of G divided by m. Well, that's really what I just did, because this right here is my F of G, and I divided it by m. So I would recommend putting this formula next to this formula on your formula chart. Okay, so put this formula next to your formula on your formula chart. All right, I'm going to skip past that because it all says the same thing I just wrote. All right, I want you to estimate the value of gravity on top of Mount Everest. Mount Everest is actually 8,848 meters above the Earth's surface. So in order to find gravity, we would have to know the mass of the Earth, and we'd have to know the universal gravitational constant, and we'd have to know how far from the center the top of Mount Everest is. And in order to know that, we're actually going to have to know the radius of Earth plus this 8,848 meters. So the mass of Earth, which I gave you in a previous problem, was 5.98 times 10 to the 24th kilograms. The radius of Earth is 6.38 times 10 to the 6th meters. So the total radius that I want to deal with is that radius of Earth plus how far is the top of Everest away from the Earth's surface. So that would be my total R value. So then I'm going to use my G expression that I just showed you when we derived it a minute ago. And I'm going to use my 6.67 times 10 to the negative 11th, the mass of Earth, which I gave you, divided by the radius plus how far Everest, the top of Everest is from the Earth's surface, and square it. So divide by that squared. Remember, don't forget the squared. So we should end up with 9.77 meters per second squared. This is important because if you realize as we increase the distance away from the Earth's center, gravity should go down because that force goes down as we decrease that. So the acceleration value of 9.8 should decrease as well when the force decreases. And if we increase the distance, then the force should decrease by the distance squared, so let me slow down. When we increase the distance between the objects, or the distance of the radius, then we are changing the force of gravity by the inverse squared. Proportionally, it'll be inversely proportional to the square of that distance change. So this should make sense that if we increase the distance, then the force was going to go down, and if the force went down, then the acceleration would also go down. So I didn't do a good job there finishing that up, guys, but this should help you do problems 8, 9, and 10. I will remind you that if you have multiple forces, that you can add those forces together, and if they're going the same direction. If they're going opposite directions, then you have to subtract them. And if the forces are at an angle, then you are going to have to look at them as x and y components to figure out how they would end up affecting things overall. So that, again, will help you with problems 8, 9, and 10. If you run into problems, come see me. Thanks. Bye.